Hello there. Start our second experiment, and this experiment is known as the scientific method, the simple pendulum. So in this laboratory, the principles of scientific method will be applied. That means no theory or model of nature is valid unless the results of the experiment can be predicted. Okay, so instead of executing the trial and error method, scientists now try to theoretically predict events in nature and then test their theories against their results in the laboratory. Okay, so if the experimental results align with the theoretical predictions, so the theory would be considered as valid and an accurate description of a certain physical phenomenon. Okay, so in this laboratory experiment, the validity of the theoretical expression that describes some of the behaviors of a simple pendulum will be explored and it will be tested. Okay, so there will be like parameters that we are going to deal with, like when we are talking about like a simple pendulum. So a simple pendulum it's just like a small mass attached to a string, and then you let it swing, and then that swing will move up, right to left and left to right. And if there's no any friction, then that oscillation or that movement is going to go ahead and then for a long time. Okay. So now, what are the few definitions that probably we need to know? Then, and what are the different theories that we are going to test in this experiment? So, according to theoretical experiments, the period of a simple pendulum can be calculated using this formula. Okay, so this formula is from theory, and then of course the numbers will continue. This equation it continues. That's what it shows. So it says that period t equals 2 pi the square root of L over G, in parentheses 1 plus 1/4 of half sine square of the angle, like whatever angle that you choose to oscillate the pendulum, plus 9/64 sine the power of 4 of half of the angle, and so on and so forth. Okay, so but this is a theoretical expression. So this is from a theory, from mathematics. It's just like the scientists is like, okay, probably the period of the scientific, a simple pendulum can be done or found using this kind of somehow a wave kind of equation. Then now the question is probably we may. So the period of a simple pendulum can be calculated from theory using this formula that I mentioned. But this period can also be approximated by a simpler equation. So, there is something which asks you, like, do you think this is reasonable to say that as long as the angle theta, we keep as long as theta as a very small angle, let's say less than 20 degrees, then this t will approximate the whole equation. T equals 2 pi over square root of L over G will approximate the equation, the overall equation. Okay. So now what I expect you to do in today's experiment is the following. So you will be doing the 3 tables. Okay. So the 3 tables. So this is what a simple pendulum is like. There is a mass attached, and then you let the mass to swing from A to B and then B to A, and so on and so forth. And the angle theta that was expressed in the equation was this angle. Okay. Now, what we are going to do is we're going to do the following. So now, what I want you to do is pretty much like you will be expected to apply like 1/4 and blah blah blah, this equation to find some of the scenarios. So for small angles, as we said, if the angle is less than 20 degrees, if theta is less than 20 degrees, just you can approximate the period using this. If the given theta is more than 20 degrees, and then you go ahead and then approximate or calculate t using this longer equation. Okay, having said that, that's pretty much like the overall idea of the whole experiment. And then you may say, like, what are we going to prove in here? So we're going to prove several things here. The first one is, like, if this theoretical period, right, can approximately be equal to whatever we are going to do in a lab. Of course, we cannot do any physical lab, but at least there is a nice simulation that we may probably use, and I will show you some of the steps there. So read the experimental procedures, and then, but you are going to use the simulation. Okay, and then, first of all, before I go ahead and then try to help you filling the tables, then what I want you to know is a few of the terms. So for instance, P, period. Okay, so the period of a pendulum means, like, time taken by the pendulum to complete one oscillation. Okay, one oscillation means like one full arcing force. It's not like just going. It's not only one way. So that means, like, if the pendulum is, as you saw in one of the diagrams, if it's like this, and if this is the angle theta that the pendulum started to move, and then it's going to swing to here. So it's going to swing from, let's say, from A, it will go to B, and then it will come back to A again. So this is one full oscillation. This is one full oscillation. That's what it means. Like, so that means the time taken by this mass, by the mass m of the pendulum, to go and then come back, that is what one period is. So the first table, what you will need to do is, like, you will measure the oscillation, and you will use a stopwatch, and then you will stop it, and then you count a certain number of periods. Okay, so in the procedure, this is what you will say. So set up the pendulum, experimentally investigate a small angular approximation. That's something that you need to do. So it asks you, like, rather than, so it says, like, data table 1, keeping the length of the mass of the pendulum constant. So for the first table, you're going to keep the values constant. Which values are you going to keep constant? The length and the mass of the pendulum, you are going to keep them constant. So for instance, I already gave you those values. So you keep the mass at 150 gram or at 0.15 kilogram. And the length, you keep it at 85 centimeter or 0.85 meter. Okay, this, when you convert it to kilograms, it's going to be 0.15 kilogram, right? Now you will be using those angles, and then you are going to carry out the experiment and then fill the lab. So just for the sake of completion, then it says here, so it says, like, rather than timing only one oscillation, to time one oscillation is always very difficult. So time several oscillations, and determine the average period for the 5 of them. Okay. Then what I'm going to do is, I want you to pay attention here, because I'm going to use the simulation that I posted. Then the first angle that is given in the table is 5 degrees, right? So even it's given in the thing. So what we're going to do is, so let's set up our length. So I'm setting up the length to be 0.85, and then the mass is 150 gram. It means 0.15 kilogram. Then I'm going to keep it. Then, because we are experimenting this experiment, it's gravity is going to be 9.81. Gravity means the rate at which objects accelerate when they are falling from a certain height. Okay, we're going to see this in the second chapter of the lecture. Now what we're going to do is, let's go ahead and then like use a stopwatch. That means this has a nice stopwatch here. I'm going to use that stopwatch, and then I'm going to take this to a 5 degree and then let it oscillate. Okay, I'm going to show you like how you do the 5 degree. So when you move this to the right, you know, see, it measures the angle for you. Then 5, this is 5. And then what am I going to do is, this is of course, you know, the error is very minimal because it's a computer simulation, but in a lab, you know, there are so many factors that may affect your judgment. But now this is 5 degree, it's precisely 5. So the margin of error is pretty much nothing when you're measuring the angle. But in a physical lab, like I'm sure that like, you know, when you read the angle, maybe you are reading 4.9, maybe you are reading 5.2, something like that. It might not be precisely 5.5, but anyway, but we are doing it. Okay, so what I'm going to do is I'm going to let it go and make sure that it's normal. So you let this thing to oscillate in a normal situation. Okay, so what I'm going to do is I'm going to time when this object comes over here, right? I'll start the timer, and then after 5 oscillations I'm going to stop it. Okay, so now pay attention. Ready, go. 1, 2 oscillation, 3, 4, 5. So in 5 oscillations I got like 9.03 seconds, right? So therefore, so when you do your lab, I already mentioned something somewhere. Always you must show at least one full calculation for every table. So for instance, in the first table, then what is the experimental period? So I'm going to show you like the experimental time that I got for 5 oscillations is 9.03. So now for 5 oscillations, right, I got 9.03 seconds of total time, right? So but the period is just only for one oscillation. That means what you're going to do is you take 9.03 seconds and you divide that by 5. Why am I dividing it by 5? Because the number of oscillations that I considered was 5. You may consider 5, you may consider 10, it's up to you. But 5 should be enough because this is more of like a simulation. If it was in a lab, maybe you could go a little higher. So therefore, I'm going to calculate the period. This is the experimental period, 9.03 divided by 5. Use your calculator, and then I'm getting a value of 1.806 seconds. So what I'm going to do is I'm going to write that. So let me see if my thing works. Okay, so then for the experimental, then you will have to write 9.806, and you are measuring the period in seconds, so therefore you have to put seconds in here. Over here, make sure that you put the given mass is 0.15 kilogram. Always when you write a name, give a unit with it. The length of the thing is 0.85 meter. So we're keeping this constant, okay? Now the theoretical. Then for the theoretical part, as it's written in the manual, it says that like for theoretical, just if the angle is less than 20, then just simply apply the equation period. So this is experimental. Let's put it as TE. So this is theoretical. Okay, so T theoretical would be calculated as 2 pi square root of the length of the pendulum divided by gravity. Okay, so 2 pi, pi is, you can approximate it as 1.13.14, otherwise your calculator will approximate it for you. The length of the pendulum is 0.85. Make sure that you are plugging this value in SI unit, because gravity, the acceleration of gravity, that is constant. Gravity is constant, okay, and approximately 9.81. So now from this theoretical value, so what you need to do for the first experiment, I already did for the 5 degree, okay, so you will have to show one, at least for the 10, for the 45, whichever you choose, okay. So I'm going to plug in those values in my calculator and then see what I'm going to get. Okay, times 2 pi. So what I'm getting here is the theoretical value is 1.85 seconds. Okay, then once you find this, so this is what I got from the theory, this is what I got from the experiment. Okay, so I got one from the experiment, second one was found from the theory. Then you put this value in the theoretical part, which is 1.85. Okay, then you go ahead and then you find percent error. Okay, the percent error of a certain experiment is calculated as following. Make sure that you go through like some of the notes in the first lab. Percent error is whatever experimental value you get minus whatever the accepted or the theoretical value is, divide that by the theoretical value, multiply that by 100%, and that's what your percent error is. So for this experiment, your percent error is going to be experimental, which is 1.803, is that what I found? 06. Minus the theoretical is 1.85. Divide that by 1.85. Then multiply that by 100%. Okay. So therefore your percent error, so minus, then divide that by 1.85, multiply that by 100, very decent percent error, 0.35%. that means like more than 97% accuracy. So this is your percent error that you get for the experiment. Very good. I mean, if your percent error is less than 10, it means like you're almost 90% correct. But in this particular case, we are 97% correct, close to that. So you'll go ahead and then write that percent error as 2.35. Okay, of course, percent. Then go ahead and then finish the table, like do all this. It's very, very easy, straightforward. Even I like the simulation. Okay, then for the second table, again, you will have to go through the manual. It's going to tell you what you are expected to do. Okay, so this is, and then in step 2, in the data table 2, what we're trying to investigate is like whether our data is mass dependent or not. Okay, so therefore it asks you like here, experimentally investigate method of the period is independent of the mass of the pendulum bob. So using 3 masses provided, So that means in the lab, okay, but right now we're not in a physical lab. I gave you the masses, and you can change that in the simulation, okay? And then keep the length and the small angle oscillation constant. So you choose an angle. I already gave you a value to start, so use a 20-degree and the length is 85. So you keep the length as it is, and let's reset this. You can call it stop and timer reset. Then keep the length constant. Now the idea is we're going to go ahead and then change the masses. So I already gave you a set of masses, and we will be using 20 degrees. So use 100 gram at 200 gram at 350 and then 380, and fill out the experiments. Okay, so now, and then you have to do everything and then write your conclusion whether the period was dependent or independent of the mass variation. Okay, so I'm going to do one more. Then let me set the mass to 100 grams. So the very first value that I give you is 100 grams, and then take the oscillation to happen at 20 degrees. Okay, all right. So we're going to follow the same procedure again. So we're going to let this thing to oscillate 5 times, and then whatever time we get, we divide that by 5 times, and then we do all our calculations. Okay, so ready? So I'm going to, on a count of 3, I'm going to start. When the mass is here, that's where I'm going to start the oscillation, and then I will continue counting for 5 oscillations as in the previous case. Okay, so ready, set, go. 1, 2, 3, 4, 5. So this is how much time that I got for 5 oscillations. Once again, so this is for the second part of the table, second table. Okay, so this work is pretty much for the second table. So now the period from the experiment is going to be, what time did I get? The time I got was 9.17. So 9.17 seconds. Divide that by 5 because we let that thing to oscillate 5 times, right? So therefore, use your calculator, and 9.17 divided by 5, then I got 1.834 seconds. Okay, so now find T from theory. Okay, so from theory you can approximate T as 2 pi L over G. So you got 2 pi, the length is, what value did we use? 0.85, and then gravity is again 9.81 meter per second square. So if you simplify this, okay, the length is 0.85 and gravity is 9.81. Then you're going to get a value of pretty much 1.85 seconds. Okay, this is second. That's the same as what we found in table 1, right? But it's for a different angle. But what we said is, in the theoretical part, for any angle that's less than 20, then this value normally it's gonna be really small, and whatever in the parentheses after this, and pendulum period can be approximated by this simple equation. Then now you go ahead and then you calculate the percent error. Okay, for each step you are going to do the percent error. Then the percent error, once again, the theoretical, which is 1.83. I already wrote the formula above, so this is just going to be a repetition. this is absolute value. Absolute value means it doesn't matter whether you get the value positive or negative, you will always provide a positive answer. Okay, so therefore percent error is going to be 1.834 something minus 1.85, divide that by 1.85, we multiply that by 100. Whew. Percent error is 0.86%. That's almost nothing. This is like a dream percent error. For when we did this experiment physically, believe it or not, most of our errors are between, like, you know, the best that we could find is like anything around close to, you know, 8, 7. The rest is just some students used to get like 20%, 30%, things like that. But this is like a nice simulation. You know, you can precisely time the motions and whatnot. So you keep on doing, and then just basically you complete the second part of the table. So once again here we chose a mass. So in kilogram, this is where you will fill in value. We're using 20 degree because we don't have to use the long formula. The length is 0.85 meter, and of course the period is in seconds. Sorry. And this is 20 degrees. Okay. So in seconds. So oh boy. So for theory, what we got is 1.85. For the other one is like 1.834 or something. That's what we found. And then the percent error is like 0.86%. Don't forget the percent symbol next to it. Okay. So this is like the mass. The mass is what? 100. Okay. Rather 0.1 because it's in kilograms. And then go ahead and then do the same thing for the second value is that I gave you is 200 grams. So do the same thing for the 200 gram, which is 0.2. And then do your experimental and do the theoretical. I don't think the theoretical will change, right? Because the equation doesn't involve any mass, so most likely that value is going to be the same. So what you will do is you will stop it and you will reset your timer and you increase the mass to 0.2. Okay, and then take this again. It has to be on 20 degrees because it has to be consistently at 20 degrees. You go ahead, you let this guy oscillate for 5 times, you stop the time and you divide that time by 5 so that you can get the experimental. So when you do this, like if the percent error stays like close to a 0 value, that means close to anything less than 5% is acceptable, very acceptable. So therefore you may say like, okay, yeah, maybe the mass didn't really matter because the theoretical and the experimental values stayed close to each other, close to 1.85. Okay, so that's what you're going to do. A little trick here is going to be this experiment. So in this experiment, what we're going to do is the following. So now we know that from theory, let's say, you can call it from theory, you know that gravitational acceleration G theoretical or G accepted. So let me start with table 3. So G accepted or that means the theoretical. It's the same as what we were using, 9.81 meters per second squared. So in this experiment, we're trying to prove if G accepted is really close to 9.8. In the third table, how do we do that? We're going to do the following. So what we're going to do is we're going to start from the period equation. So the period t is equivalent to, we know that it is 2 pi the square root of L over G. Now, if we do some rearrangement, we can isolate G from here, right? How do you do that? You can square both sides, for instance. If you square this side and then if you square this side, you're going to get this, right? T squared is equal to 2 squared is 4, pi squared is pi squared. The square root of L will be L. The square root of G is going to be G. So now, once we rearrange this, if we go ahead and we have this t squared, and then to isolate or the equation to write it in terms of L over G, in terms of L, what would happen is basically like we can eliminate some of the parameters, and then eventually we will have let me lower this side. Then if we eliminate like everything like on this side, and then finally we will have an equation which is equivalent to L equals G is cancelled, 4 pi squared is cancelled. It's going to be L equals G over 4 pi squared times t squared, right? So this equation, if you look at this equation, this is a linear equation. This is a linear equation, but you may say like, but we have t squared and everything, why do you call this a linear equation? So the reason is, this equation can be similar to an equation like this: y equals a times x squared, or a times x. So what happens is, like, this a is going to act like the slope, right? So this is a linear equation, it's similar to a linear equation. Y stays as y, and a stays as slope, and x is of course the independent variable. Y is the dependent variable, right? So from your algebra class you already know this. Then now the question is, what if you do the following? You have all your y values. Your y values are your L values, right? That's what they are corresponding with. And all your x values, that they are correspond with your t squared values. Then your slope value will correspond with G over 4 pi squared, isn't it? So that means if you graph L versus t, or the period squared, what you are going to get is literally a linear graph. Linear graph that's somehow represented by this. So if you do the graphing, like let's say you have your x and y, and on the y-axis you put all your L values that are given in the data, and then all your experimental t squared values, right? And then you put them in there, and then if you do a good job in terms of plotting the graph, you can use software, you can use Excel, you can use an online software to do the job for you. Then this graph has to be, as much as possible, a nice straight line. And the slope of this graph must be equal to G over 4 pi squared, right? Then from here you can find G, which is equal to, you will get the slope because you will do the graphing, and then 4 is known, pi is known, and the pi squared. From here you will find G, and that G is your experimental. Okay, so your G experimental is found. Once you find your G experimental, and then you proceed, and then of course you already know your G theoretical. How much is it? Your G theoretical or accepted, which is 9.81 meter per second squared. Then you compare those two using the graph. I mean, using the percent error. If you find the slope of this graph, if you do it in Excel, you will find it. If you didn't do it in Excel, you want to do it manually, take 2 points, 1 point here, 1 point here, and use that x1, y1, and use this x2, y2. And from the very first experiment, we know that slope can be calculated as y2 minus y1 divided by x2 minus x1. Okay, so this is for recurring. I'm doing it a lot faster, but you can pause it anytime you have any doubts, and you can do that. Okay, the overall idea is the following. I gave you a set of so angle and mass. I already told you, like, just use a smaller angle to be to simply use the easier equation. Without use 150 gram or 0.15 kilogram. Okay. Now, what you need to do is length. The very first length that I gave you a set of length. So, 85, 60, 45, 100. Okay. So 85, for instance, 0.85 length. Let's experiment it. It's not a big deal. So what is the mass? I'm asking you to use 0.15. Length 0. Now the angle is 15. If you want, you can use 22. Okay. Then let it swing. I'm going to start now. 1, 2, 3, 4, 5. So I got like 9.39. So I got the value is 9.39 that I got, like, so divide that by 5. 9.39 divided by 5. That's the experiment. 9.39. So which is 1.878 seconds. So this is T experimental. Then the theoretical is going to be pretty much the same thing because we're using the same length. So T theoretical is 2 pi square root of L. L is 0.85 meter. Then gravity is 9.81. So that's 1.85 seconds, right? So find the percent error between the two. Okay. Then that will be 1.878 minus 1.85. Divide that by the theoretical 1.85. Multiply that by 100. Okay. So divide that by 1.85. Multiply that by 100. So the percent error is 1.5. That's very minuscule for a percent error. So here we got the period to be 1.878 and the percent error is 1.5. And the time, you need to square 1.87, okay? 1.878 square, which is 3.53. Okay, and then you do the same thing for the only thing that's going to change is 0.6. The length, you need to change the length of the pendulum. Then you stop this, reset your time. Length now is 0.6. Okay, you proceed like that. Now again, start at 15 degrees, you let it swing, and then you start your timer, and then after 5 oscillations you stop it. That total time divided by 5, that would be your period. Okay, you will do for the remaining 2 more length, so for 0.6 meter, and then for 0.45 meter, and then for 1 meter. You do this, you fill out the table, you do the graph. From the slope, you get the answer for gravity. Then whatever gravity that you get here from the graph, from the slope of the graph as it says it, then find the percent error. So I don't want you to do anything else. I don't want you to answer any questions. Just simply give me those 3 tables and a graph, then you're good to go. Okay. If you have any question, as always, of course, you can always ask me. In the meantime, have fun.